So where are this parts of the code for the expectation value of position and momentum? Okay, so this is in line 217. See, it's probability multiplied by this x capital, and then you put summation, right? And in order to analyze the change of the position along time, we need this another line that accumulates this. So it's called AVG here. It accumulates in variables that has it added again and again and again. So if we open a new figure and plot you'll see some change of the position. Right now it is curly because I didn't remove the potential, and it reflects and goes back, starts going back. But in the last question that we are going to go over today, we will briefly consider changing of the potential and running it to for several models. Basically, when you go for the rest of the semester, we will do projects when everyone will select his or her own potential and investigate a problem, specify the potential in the same way. So whoever, I know who it is, who will be doing these applications, you'll open the door for the whole class for the last month of the class. So there should be additional variable for the same variable. All expectation values, all observables are computed at least twice, because there are different methods, and some are computed 3 times, because there are 2 reliable methods, 2 and 3, which are universal, and there is one method that will work only for free space, but it is used as a reference point. So this trick of making only multiplying by probability is possible only for diagonal operators, but if we do have operator that is off diagonal, like momentum, we need to practice more general definition. So there should be a variable that would implement the expectation value of momentum. And let's look through the code and identify what it is. Here they are. So 223, we multiply, so it is by second method. We multiply the vector corresponding to wave function conjugated at given instant of time by momentum operator, which we know is a matrix, right? And then we multiply it by the wave function once again. So here we do not have summation sign because here the MATLAB does practice. Here MATLAB does practice row by column procedure. So the conjugated wave function is row, px is a matrix, and not a regular wave function is a column. So psi at point 1, psi at point 2, psi at point n. Here the matrix for momentum, and then psi at point 1, psi at point 2, psi at point n. So this equation is implemented to the line to the D3. Couple of lines later, there is a trick to accumulate values, expectation values of momentum at each point of time. So if we would try to explore this original variable, it will have only one value that is not helpful for us. It's maybe only the last. It is a future, but in one point. But we are ambitious. We do not need just one point of future. We need the whole trajectory, how it gets there. So if you plot this AVP, it should okay. Here we did experience a little specifics. I wouldn't say it is good or bad. When I blindly tried to plot the trajectory of momentum, you did see that it was some noise, not useful. So the procedure for computing expectation value So the procedure for computing expectation value deals with wave functions which are complex, which have imaginary and real part, and also momentum does have real and imaginary part. Even if we know by our scientific intuition that momentum is expected to be real, there is the variable itself is complex and it has imaginary part which can be negligible, 10 to the minus 16 compared to actual value. But if I blindly try to plot it, it will show some strange thing. But if we neglect this imaginary part and plot only the real part, then it will look reasonable. if one would plot okay, so if one would plot both position and momentum on the same axis, and one needs to scale them by the values corresponding to 1 over delta x, which will in this case will be around 100, you'll see that you already know from your previous experience, and you kind of can intuitively expect that if position changes quickly, then velocity is constant, if it is a same slope. And if it slows down, then velocity goes to 0. If it turns back, then it will start growing again. So by plotting at the same time expectation value of position and momentum, one would illustrate an analogy between quantum mechanics and classical intuitive expectations. So in many cases it is possible and reasonable. In some it fails. So uncertainty values. What is this? Have you ever seen expressions like this? Not in this course, but in your general education. Life experience or academic experience. In preparation for labs, for processing experimental data. Like making summation, then dividing by something, taking square root. Yeah, standard deviation, right? Yeah. So we are practicing an analog of standard deviation from quantum point of view. Excellent. Micro plus 1. So if we put here the wave function with star and without star and do dx and make integration, it will be a standard deviation. Deviation of what to where? What does it tell us? We already covered it in class. We already covered it in class, and we did some homeworks about this subject. So if your wave packet is not ultra thin peak, but has some width, there is a expectation value of position is where the center of the distribution is, right? And this thing computed according to this formula will show how far the wings of this distribution are going to the sides. At time 0, this width parameter is defined by whatever we placed in to the initial wave function. And I think if we jump to the first 5 lines of the code, it will be x var variable. But then, as time passes by, as your wave packet moves forth and back, the width may shrink, or more often it expands. So it is an important variable, right? In addition, if you would remove this, expectation value of position, then it will be an equation for expectation value of position energy in case the potential is harmonic, right? Where it is defined. So let me invite you to the line number 218. And since any polynomial of position in the position representation will be diagonal operator, here one practices the same trick. Instead of doing row by column operation, one is just taking psi star psi, which is probe variable, and then multiplies it by the position minus expectation value. So this is the vector and this is a number. Make sense? Line 218. So if you will, and let's focus our eyeballs a couple of lines below. So if you look on the variable which has plural at the end, variances, so it accumulates the variance at each time step again. So if you want to look at the width of the wave packet as function of time, we may plot variances. Well, although there is some potential, there is not much surprise. It agrees with what we have seen for free space. As time passes by, the variance, the width of the wave packet increases. Here it increases even quicker because it bumps it collides with the barrier and part of the wave packet stays near where parts gets back, and variance, even if the distribution is not, like if it is not a single hump camel, but if it is two hump camel, it will still look in the middle between them and compute average variance, which will be not an ideal characteristic, but still the procedure would work. So, how did Werner Heisenberg call it variance? And design the principle. Yes, perfect. Gauge +1. So, if the distribution is very narrow, position is certain. If it is distributed, it's uncertain. So the value of this variance is measure of uncertainty. Uncertainty of position. Right? Guess what I'm going to do? There are conjugated variables that try to come in couples. If you have position, we correlate with momentum. And if you have uncertainty of position, we should look at uncertainty of, yes. So let's look over the code and identify where is the uncertainty of momentum. Would this equation be a good representation of uncertainty of momentum? So it should be interpreted as psi star momentum operator minus expectation value of momentum square times psi dx. So sigma sub p, right? And a couple of lines below, there should be a piece of code to accumulate values of this uncertainty of momentum along the code. So it is ASP. Here is the average SP in the line 228. So if we are curious in the expectation value of momentum, we may want to practice plot of this EVSP. And same thing as before. If I plot this expectation value of momentum directly, it immediately comes up that all variables or most variables here are complex, and there is a noise, even if it has show imaginary. So it is multiplied by 10 to the minus 13. So it is negligible, but it screws up because each variable is two-dimensional. One axis is real and another axis is imaginary. So, and here we need to focus only on the real part. For this specific case, if you have seen the movie, when you run, you see that there is a barrier, and wave packet it bumps into the barrier. So when it bumps into the barrier, it kind of smashes and becomes more narrow, but then it reflects and becomes broader again. And if one would want to numerically prove right or wrong Heisenberg equation or Heisenberg uncertainty principle, one will need to multiply these two variables and plot them versus time and see if it ever gets smaller than one constant square. Probably the project. So we are done with part that will be presented by Dion and Gage. Right? These four points. I'm going to make circles around the classroom and see if you were those of you who decided to practice these variables, if you were successful to do it. And I will also take a breath for next question.
Yeah. Yeah, I know I might have some questions later on. So,
And let's say that we do
yeah. Yeah.
Cool, sir. We kind of plotted real and imaginary parts of wave packet last time, right? Did we? You don't remember?
Oh, yeah, Joey. I got that stuff. That's all right. Pictures. Okay.
Let's quickly go over it because it is fun for some people. So if we decide to plot real part of wave function, it will be ugly, right? Oscillating too much. Maybe one should start with C0. So when I see it for the first time, I decide that I was someone was lying to me. There is a promise that wave function is Gaussian, and this form is something a little bit more exotic, right? But if we if you plot both real and imaginary, they also do not give us expected Gaussian. But if we add them together, so I'm just lazy to type it in, but basically it is same as finding radius. You take x squared plus y squared and then square root, right? Length of vector. If you do the same with real and imaginary components, real squared plus imaginary squared and square root, it will be length of a vector. And it is abbreviated with absolute value. Absolute value of C1. happy with me. Okay, then I will probably will plus usually no, it was different thing. I just forgot to put independent variable. Yes. So if we add the absolute value, which means real square plus imaginary square and square root of them, so the distance from origin to both of these components, then it will be smooth Gaussian. So when we try to visualize wave function, it is sufficient to plot real and imaginary part, but sometimes it could be confusing. It is more reasonable to provide envelope function, which will be like absolute value, or real square plus imaginary square square root. Probably, if we did it last time, probably we also tried to redo this figure with different value of initial momentum. Did we? Did we try to redo this figure with different value of initial momentum?
Yep.
So it will be, if you have to present this subject, it is really, how to say, enlightening to your audience. So if you show that one can get different amount of fringes and correlate it with the P0 parameter with original momentum, it becomes really illustrative. Now you remember it, right?
Yep.
Okay. Done with visualize real and imaginary. Visualize potential and probability distribution. So I'm going to do something. Well, this question, visualize potential and probability distribution, it is something really trivial that everyone can do without me right now. But I'm going to focus on it because it is very simple but helpful way to intuitively analyze behavior of different quantum systems when we will try to do research projects. So, in some sense, there are not too many parameters. Most of the machinery of this code is already determined. We know how to construct Hamiltonian evolution operator. There are only maybe 3 things that one can change. One can change potential, which will determine which system you describe. One can change initial position of the wave packet, and one can change initial momentum. The rest is kind of standard. And then, depending on the potential, which may have dips, wells, barriers, the wave packet will go to different sides with different speeds. So the curvature of potential means a lot. And if you have seen the movie that pops up when you start running the code, it shows simultaneously potential and wave packet. So it is, I don't know if it is a big or small science, but it is really catches up mind of a human being. It helps to analyze what is going on. So the potential should be stored in the variable v. Let me check. Yes. And wave function should be stored in the variable, not wave function, but probability distribution. Okay, so this is not yet a complete practical prescriptions for solving any problem in or quantum field is important. But it is mostly closely related to real life too that we will practice in the course. So later on we will be able to construct potentials that will describe semiconductors, solar cells, chemical reactions with activation barriers. It's all of these things can be rephrased in terms of one-dimensional potential. And then depending on how the wave packet attacks the barrier or drops down into the well, one can describe most of the phenomena that one observes experimentally. So we are not going to quantitatively describe everything in the world, but you'll be able to qualitatively describe most of the fun processes in modern science. So in brief, you just plot two functions, two vectors, two variables with the same independent parameters, right? Is there any challenge or wish list? What could we do in order to make it more intuitive? Any thoughts and suggestions, or it is fine as is? What is Boltzmann distribution? Boltzmann distribution. You should have it in second semester of freshman chemistry. When you get through gas laws. No? The higher the energy of a state, the lower the probability that it will be reached. Therefore, the dust is typically on the floor rather than on the top shaft. So it's Boltzmann distribution. I do not want to dust my floors because my house doesn't obey Boltzmann distribution. What is activation energy for chemical reactions? Okay, so it is a critical energy that one needs to overcome in order to launch the reaction. There is a threshold. How does energy of what should be higher than activation energy? Yeah. Yes, but if you repeat experiment again and again, once reaction goes, another is not. It doesn't go back. Reactants are the same. How do you reach activation if the reaction doesn't go? Catalyst, what else? It's great, but what else? Most cheap. What? I can hear it from science. Yes, heating up. So if you heat up reactants, the activation barrier will be reached and reaction will go. If you turn on the stove, so so what does it mean temperature? What does it change when you increase temperature? Yeah. Which energy? So how many for potential? How many for kinetic? Majority. Kinetic. So what does it mean kinetic energy? Huh? Energy of motion. Just momentum squared, right? So look, mv squared over 2, or p squared over 2, right? So if we do have a barrier and we need wave packet to be activated, like to go over the barrier, it means that we need to assign higher momentum. If the momentum will be higher, the kinetic energy of the wave packet should be bigger and it should overcome the barrier, right? But right now in this figure, do you have kinetic energy anywhere? It's a little idiotic question from me. We didn't request energy anywhere. We put V, potential energy, and we put probability distribution. So in a way, for intuitive analysis of reactions, we are missing important portion. We are missing kinetic energy. And you already told it to me that the higher the momentum, the higher kinetic energy. And the overall wave packet should be higher than barrier. So why don't we try to offset this line of the wave packet by the value of energy? We already did it when we were representing eigenstates of particle in the box and harmonic oscillator. We were offsetting the wave functions by the value of energy, right? So if you would try to add energy to this probability, and this energy will depend on initial momentum that we assign, then this will become very helpful intuitive tool when one can get analysis of the expected processes and predict the future in the quantitative way like a snap. Does it make sense? Okay? So what should we do in order to practice this plan? We need to find expectation value of energy, right? Which could be formulated, for example, as putting our CHEM, which is not food but Hamiltonian, and maybe putting wave function star multiply by wave function, and telling that it is expectation value of h, right? And then upon practicing this equation, if we are suspicious, we should compute it at any time step. If we are naive and trusting, we can compute it once, because there are theorems that there is conservation of energy and it shouldn't change. But who knows? We may double check it. But whatever, computing it once or several times, we would put this expectation value of Hamiltonian as an offset for this probability. And then if energy will be high enough, it will just shift up the energy and will show that it will be over barrier, and then we will see whether it will go over or not. So I think the person who was writing it, and most likely it was me, was naive and not suspicious. So it is computed only once, trusting that energy conservation holds. So E2 and E3 in lines 326 and 327 are expectation values of Hamiltonian in version 2 and version 3 using appropriate wave functions. So let's try to add this E2 and E3, well, E2 if you use the second method for probability. our energy is imaginary. Okay. See, it becomes a little higher compared to what it was before. Let's maybe double check. X, comma, probe 2 without do dashes. So due to adding energy because of the motion of non-zero momentum, we offset from 0 by like 0.05 of heart rate energy. So 0.05, it will be about one electron volt. So substantial energy. And here we see that when it bumps into barrier, there is a little passing through so-called quantum tunneling, but mostly it is stopped by a barrier, right? I'm going to practice a little thing. I'm going to increase momentum 2 times and redo this figure. Yes?
Why is the kinetic edit brought to instead of B?
Question. In fact, here I did add together not kinetic but total energy.
Oh, okay.
Kinetic energy would change. There are 2 different things. It's a perfect question. There is an operator of potential energy, and there is expectation value of energy. So this V here is a function. It's just potential as function of position. And this E2 is average energy, which is 1 for the whole wave function. Okay? So depending on initial momentum, we can make our wave packet so energetic or not energetic. And then it will consistently shift the whole wave function, upper or lower. This is only visualization. The way we computed expectation value is just a number. But we consistently add, we are mixing apples and oranges. We are mixing, on the y-axis we have simultaneously probability distribution and energy.
Oh, okay.
So it is like a heresy.
So is the V like this one?
This is X. Let me be specific and just type it. X label position.
Okay, but is the like the blue graph? Is that one like?
It's V. It's
by
V
Oh,
of X.
Okay.
V of X.
Okay. I was just. Yeah, it's fine.
Uh-huh.
I was thinking of it backwards.
And y-axis will be probability distribution and energy. This is not literally and rigorously correct, but everyone does so because it is really helpful intuitively. Then you look on the image and you immediately catch the whole process. So I'm going to redo the same figure by running the code with different value of P naught. So it was about 0.4, but we do it like 0.6. I do not need to ramp it up too much. Save. So in this movie, the energy is not offset. See, it goes over 0. But you see qualitatively some part of the wave packet passes through. So it's half goes through, half reflects. let's.
So that green line represents the energy barrier.
Yes. So it is our old figure, and I'm going to. Which colors were okay? We didn't have a green color. Green. See, we have increased the momentum maybe 50% more. It was 0.4, we made it 0.6, and energy grew substantially. So wave packet is definitely above the barrier and now allows some transmission through. And it's no wonder 1.5 squared will be like 225, so it's more than 2 increase in the value of energy. So we did real and imaginary part. We did potential energy and probability distribution. Why there are 3 of them? Well, there are several methods, right? There is for which depend on how we define the momentum. I know it is. It will be a little waste of time if you do right now, but additional 5, 10, 15 minutes, and you will find out variables for third method, right? They are located nearby. Visualize any observable. That's trivial. You just plot it. Find where it is accumulated and plot it or save it. Organization of data bundling groups of observables. So suppose that, well, not suppose, you all are very busy. Maybe the third year of undergraduates is the busiest time in life. And suppose that you do not have time to listen to this mumbling and find command line codes to bring up specific variable. So for this situation, when you run the code, you see that there are popping up panels with several images. Some people find it useful, some find it ugly, but most of variables are already plotted. So if you look through this groups of variables, they're kind of labeled and analyzed. So position, momentum, uncertainty of momentum, and there are several lines because there are calculations of these observables by three methods. One, by pure, mostly theoretical formula, which is for free space, when there is no potential, so it is as dashes. This line is not shown for expectation value of momentum because momentum will be conserved if there is no potential. It will be just straight line here. And for position, it is a straight same slope growth, and for uncertainty, it will be square of time. And this orange and blue lines are observables computed based on method 2 and method 3. So if they are not equal, it means that something is not perfect, but still we can use it for analysis of models. If one really hunts for precision, one typically can use smaller time step, smaller grid point on position, smaller x step, but then one needs to have more of those points, and it will become more and more expensive. Right now we are running single passage of a code within less than a minute, but you can easily make it to work for like 10 hours, if it is your goal. So, let's look what else is here. This is a good thing. I probably should talk about it. It's not a true variable, but it is a important characteristics that every chemist would like. So basically, we are splitting the simulation cell in two halves, and look for the integration of probability in the left part and right part. So in case it is a chemical reaction with a barrier, it will be reactant and product, right? So when we start and we repeat it at each point of time. So when the wave packet is on the left part, the probability to be on the left is 100%. Then when it passes through the barrier, there is a probability to form reactants, right? So amount of probability of reactants, probability of products. If it will be complete 100% yield of reaction, they will intersect and products will go to 100%. And here is like, whatever, 30% yield reaction. I will bring up a line of code that does it. So I'm going to cover two things. Where this is shown in the code, and another how to make up several panels in one figure if one needs it. Okay, so we set up the variable x2 as a midpoint in our grid points, and then we add together all values of probability distribution from 1 to this midpoint and call it probability on the left, and then we add together all values from the midpoint to the number of points, which would be this probability left will be integral from x0 to center, and probability right will be integral from center to x maximum. Of wave function squared. If you would integrate from the first point to the last point together, it will be 1. If you do half and half, it will be whatever we get depending on how reaction is going. So it's one thing. Another thing is how this multi-variable plots you just put X, Y, horizontal, vertical, and then you have several lines on one point. If one does need to put several panels, you saw this, one figure with several panels, it is done by subplot command. So 3 panels, 3 by 1, that means 3 as a column, panel number 1, and then you plot whatever you need. Then 3 by 1 grid, panel number 2, and you plot whatever you need. I don't know if you need this. Visualize any observable. I think we are done with this. Michael? Is it was good? Okay, I'll make a circle, see if anyone has questions. Take a breath, and then we'll focus on movies and applications. I need one.
Yeah.
I will need a couple of minutes to prepare the show, and then we'll go to movies. attachments. So there are in the set of codes that I was sharing a couple of weeks ago, there were like 3 versions of the code, right? And one of them has like video lab number 9. Try to open it. There is no big challenge. We can add appropriate commands to our favorite version of the code with comments. It's like additional 5 lines. But for the sake of time, I'll better demonstrate it on the one that is already has these features. So you can, for your future works, you can either to start with the version of the code that already has enabled this video processing, or just copy these lines into the code that you're practicing. So there is nothing scientific, it's just MATLAB stuff. So you need to open the file for writing, define the file where you will be storing your animated movie, and then so it is 2 commands. First you open this video, you define this video object, and then you open it. Then inside the cycle, you do need you can do several commands before you get into cycle, but things will work without it as well. What is important is that inside the loop, inside the cycle, you are doing, let me show it, to catch the screen again and again. Yes. So here are the commands. If you do not make this short pause, it may go too quickly. So you better put some simple pause, and then current frame equals get frame, and then in this right video you are adding the screen capture from a current step to this video object. I think Bill was explaining it to everyone last time, and if everyone was not too tired and attentive to Bill, we all should be masters of this video preparation, right? And after the loop has ended, you need to close this video object, right? And then if you look into your directory where you were practicing, there should appear the file that you have requested. And if it was a healthy file, you should be able either to include it into PowerPoint or upload it to YouTube, or do both. Let's check. Insert video, and then navigate to let's try if it will work with YouTube. I need more time. Okay, partial success. Maybe because I was not patient enough to wait until it is ended, and if you change aspect ratio, it is corrupted. But generally, it should work. And in addition to this lines of code, it needs patience. So, who is presenting the subject on the Is anyone signed up to the subject? Okay, then we should assign it either to Michael or to Isaiah. Okay? Huh? What is the rule of the game?
The last person to touch their mouse goes.
Well, he has 2. No, you have 2.
I have 2.
He has 3. So
Oh,
to have
yeah.
even, and it is not
That's fair.
right. And it is not too challenging. Just probably everyone already has the skill, but it's better to repeat it again and again. That when it will be time to practice it for actual research, no one will have delays. And if you try to do it and share your story of success and failures, it will be good. See, like I had some story of failures right now. So like changing aspect ratio screws up the rest of the beginning of the video. And when it will be time for research projects and presenting them, you realize that it will be no time to make actual running of the MATLAB while you are staying at the podium, because time is limited. And animations are the best way to represent this dynamics and your prediction of future. So it's good to have an ability to record it and store it and show it quickly. let's give. Oh, now it works. Good. Okay. Whew. I feel better. So, box, finite, infinite, barrier, and harmonic oscillator. Well, whatever you do to the variable v, and you know, if there are more than one definitions, only the last one does work. If you define it 50 times, everything except last one will be overridden. It's like in arguing, like, my word was the last. So if you multiply it by 0, whatever it was, multiply by 0, save as, it will be free space. So so right now, see this barrier did disappear, and both lines show propagation with the center goes forward linearly and width increasing continuously. By the way, if you are going to present this several examples, maybe preparing animations would be a really good thing for each of them, because you will be limited in time and there will be not much to. Without animation, it is much harder to explain. Maybe only Michael would survive with his skill of hand waving. And this stuff of reactant and product is kind of ridiculous and doesn't make sense. Of course, the wave packet goes from left to the right part of the simulation cell, and it is 100% yield reaction. So, see, there are commands once. So it is a command to populate an array with ones. Like if I type ones 1,5, what I'm going to get? Guess what? You can do this experiment yourself. It didn't work for me. Should one put one or comma between them? I'm wrong with spelling. Good. So, if we need to define the simplest potential for chemical reaction, like reactant, product, and barrier, we can tell that there is a certain value of energy at the initial part, reactant. There is a certain value in the center and the third one. But it should be more than 1 point. It should have ability to move across. And therefore, we populate the space until the beginning of a barrier with once. Later on, we are where is okay, so we define 3 segments. So the x2 was defined somewhere as a midpoint. This one is the, there are 3 segments, left, center, right. This 2 times AB is the number of grid points dedicated for the barrier. So how many ones will be in the center. And then at the rest, it will be also substantial, the right amount of grid points, so that the whole length of a vector will be of the same length as grid point in our x. Okay, and then each of these ones is multiplied by constants, which would determine reactant barrier product. So from now on, you can stand up with the class, forget about grades, and start earning money by science. You already can. Just have a laptop with method and a little of scientific intuition. So you can look into experimental data or intuitive assessment of values of activation energy from experiment. Energy of reactant, energy of activation energy, energy of product, and then with this code you can predict the rate, how quick reaction will go, and then you sell this data to your experimental collaborators, publish papers, pull money from federal grants. So you're already in the deep lab. Of course, it's not always successful. There are some difficulties, as in any activity, but in principle, you are already making a step into and Isaiah will help us to go through this.
Try my best.
Right. It would be really interesting to, if time allows, to quickly look at the trends and summarize what are the typical behavior of the wave packets with one or another type of a potential. So if it is free space, it just goes continuously. If it is barrier, it can either reflect back or overcome the barrier. What if we put here big negative number, minus 3, and here will be class. it's a trap. Well, in scientific sense, right? So if the particle is getting attracted to some really energetically favorable, so it's maybe capture of a molecule by a catalytic agent before any reaction, or just association reaction. There are certain positions in space where it is mostly favorable to reside. And here we see that something is captured inside this trap and some passes through further. So, which subject are we covering in the class right now? Which model? Yes. So, how should we change potential to describe oscillations? What is the potential for oscillator? What is the potential energy for harmonic oscillator? Which function? No, much simpler. Much simpler. Potential energy for harmonic oscillator. Just x squared. Parabola. So when we go to left or right from equilibrium, energy growth. Right? So if we want to practice it, then we need to go to the place where we define the potential, and instead of this barrier, we can just maybe uncheck one of those. So x squared will be sufficient, but we are starting our grid points not at zero, but not at negative. We are start at zero. And if we would put x squared, it will show only one whisker. Right? So we need to put some equilibrium position in this unit. So maybe center of our simulation cell. And with a little effort, one can find appropriate rigidity constant that would model realistic situation. But for the first run, one can just arbitrarily put some numbers and see if they make sense. This is not generally right. When better target aim before shooting. But we can try to see what happens, and if not, maybe just adjust the number on the phone. So what do we see? We put center of the parabola at certain equilibrium distance, and then we started wave packet being with bond being contracted, shorter than the equilibrium distance, assigning some distribution, some initial momentum. Then it was going downhill. Probably if you would follow momentum, it would accelerate. And then as it goes further up, it goes uphill, it feels resistance, and it getting pushed back. Then it starts moving backwards and then oscillates forwards and backwards. Right? So if we look on this accumulation of several observables, So position starts at 30, goes towards equilibrium, goes a little further, then returns back, and then starts oscillating further. So it's just one oscillation. Well, to get an oscillation, one doesn't need quantum mechanics. It's simple. But there will be additional effects of quantized implications of the consequences of quantum nature of nuclei onto motion. Then here we started momentum more than zero, non-zero momentum, but then it kept accelerating because it was going down here. Then it started stopping because it passed the center and started to experience resistance, and then velocity started to go down, 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 and then becoming negative, which means it started returning back. Then it was, at some point, it was reaching the maximal negative, and while approaching this, velocity started approaching zero. So at this point, velocity is zero. And then it started accelerating to positive side, and velocity was growing. What is encouraging that calculations by method 2 and method 3 are not much divergent. They're diverging, it's normal, but they show same trend. Again, this least successful version of code that I was running here for like 10 minutes, it uses much smaller time step, much larger number of grid points, and there the discrepancy between methods is much smaller. It is possible, but it is a burden to human patience. And for all and for all models that you run, one can suddenly get into a discovery or some interesting trend by looking on either one of observables. So if we are modeling some existing experiment, then we do have a prompt what to look at. If you don't, we can just look on several standard observables and see how they look like. For example, if one would look onto uncertainty of position for harmonic oscillator, you will notice, you might have already noticed it, that instead of expanding forever, it will oscillate. So this uncertainty will grow and then shrink. And there are experiments that confirm. Yes, I like this figure. So this image is to some sort a replacement of a movie. So if you fail to make a movie or you want to duplicate it, or maybe some papers or written reports cannot include movies, you plot this the distribution, probability distribution as function of position and time simultaneously, right? And if you do it for a couple of models, you immediately see some general trends. Like for harmonic oscillator, it oscillates. For free space, it just goes linearly. For a barrier, it will split on two branches. One pass through, another reflects. Okay, I'm going to make a circle and check if everyone is happy. But basically, we covered everything that needs to be presented on Friday. So I'm staying here to answer questions if needed. If not, if someone is going forward to request treats, then we're done.
So, like 10 cents a piece. Seems like a super idea. 3 pieces per piece. Yep. $60. It's like, what is it? Okay, good.
So saving, yeah, can you put it really quick, but it's just basically kind of like what Michael did in the presentation, right? Or, okay, so it's just similar to that.
Because if you are, we cannot predict what our careers will be. If you find yourself in the future in research and development of a company, and people with whom you will request data and analysis on origin or Excel, then you need to
Okay,
methodology.
okay, so as long as I do something similar to that.
When do we have to present your stuff?
Friday. Present at 11 on Friday. Submit PowerPoint slides by midnight on Thursday.
Yeah, but how long are we allowed to have our presentations be?
50 minutes divided by number of people. Right now, I think there are only 9 people who are continuously going. So it's like 5 minutes total, which means like 3 minutes presentation and 2 minutes questions. There are tricks. If you hate questions, you can make it a little longer. But if you make it too long, your classmates will be upset on you for taking time. Well,
Sorry guys, I got a lot to say
That's
apparently.
fine.
that's fine. Okay, maybe they appreciate it. Oh, thanks much for.
See you
No
Friday.
problem.
Mine doesn't look like that. When I mesh it.
But it's not harmonious later. It's a very. I received the.
But,
Smoke variant. Okay.
why?
How do we get the harmonic one? Yeah.
Oh, I didn't, that's working.
Oh, that's right there.
I still had
Okay, I was gonna walk with you
earlier.
Oh.
No.
Wow, man, I'm going.
Yeah.
Your call will be disconnected.